Welcome to this lecture on one of the most fascinating phenomena in nanophotonics, bound states in the continuum. Today we're going to explore how a structure that seems like it should radiate can trap light with extremely high quality factors. Let me start by presenting you with a paradox. Imagine you have a nanocavity, a tiny optical resonator that sits in free space, surrounded by a continuum of radiating modes. Classical intuition tells us that any confined mode should leak out and radiate away. But bound states in the continuum defy this expectation. A bound state in the continuum is a localized optical mode that exists at the same energy as extended radiating modes, yet remains perfectly confined without coupling to those radiation channels. It's as if you have a particle trapped in a box with open doors, yet it never escapes. Here's the situation. We have a nanocavity in the center. Normally, any light trapped inside would couple to the surrounding continuum and radiate away in all directions. But in a bound state in the continuum, the light remains trapped despite being energetically allowed to escape. This concept isn't new. It was first proposed by von Neumann and Wigner in 1929 in the context of quantum mechanics. They showed mathematically that bound states could exist embedded in a continuum of scattering states. But it took nearly a century for this to become experimentally relevant in photonics. Now you might ask, why should we care about bound states in the continuum? The answer lies in the quality factor. The quality factor Q describes how long light stays confined in a cavity before leaking out. The quality factor Q equals omega times the stored energy divided by the power loss. A higher Q means better confinement. Equivalently, Q equals the resonance frequency omega divided by the line width delta omega. For a bound state in a continuum, the line width approaches zero, so Q diverges to infinity. There are three primary mechanisms by which bound states in the continuum can arise in photonic nanostructures. Let me walk through each one in detail. The first mechanism is symmetry protection. This is the most intuitive and commonly implemented approach. The idea is that if your structure has a certain symmetry and the confined mode has a different symmetry than the radiation channels, they cannot couple. Consider a symmetric photonic crystal slab. If the confined mode has antisymmetric field distribution, while the radiation modes are symmetric, they cannot couple due to symmetry mismatch. This is a symmetry-protected bound state in the continuum. Let's think about vertical mirror symmetry. If your slab has mirror symmetry in the vertical direction, modes can be classified as even or odd. An odd mode cannot radiate into even radiation channels. The overlap integral between an odd confined mode psi odd and an even radiation mode psi even equals zero. This orthogonality prevents coupling, creating a bound state. The second mechanism is more subtle and involves interference. This is called a Friedrich-Wentgen bound state in the continuum, named after the physicists who first described the mechanism. Imagine you have two resonances in your structure that both couple to the same radiation channel. If their coupling amplitudes have opposite phases and equal magnitudes, they destructively interfere, creating a non-radiating bound state. The total decay rate gamma total equals the square of the sum of individual decay rates gamma 1 plus gamma 2. If these are equal in magnitude but opposite in sign, the sum is zero and we get a bound state. This mechanism requires careful tuning of your structure parameters. You need to adjust dimensions so that the two resonances arrive at the same frequency with precisely opposite coupling phases. The third mechanism involves topology and inverse design. This is the most modern approach and leverages concepts from topological physics. In momentum space, bound states in the continuum can be characterized by a topological charge. This charge is an integer that describes how the polarization vector winds around the bound state position in k-space. The topological charge Q equals 1 over 2 pi times the integral around a closed contour c of d theta, where theta is the polarization angle. This charge must be conserved, making the bound state robust against perturbations. Now let's discuss something quantitative. How does the quality factor scale as you approach a bound state in the continuum? This is crucial for practical applications. Let's say you have a parameter alpha that tunes your structure. At alpha equals 0, you have a perfect bound state in the continuum with infinite Q. What happens when alpha is non-zero? The quality factor scales as 1 over alpha squared. This inverse quadratic scaling is a hallmark signature of bound states in the continuum. Even small deviations from the bound state condition give you extremely high Q values. Let me give you a concrete example. Suppose we have a photonic crystal slab operating at 1550 nanometer wavelength. We want to estimate the achievable Q factor. The wavelength is 1550 nanometers. The angular frequency omega equals 2 pi c over lambda, where c is the speed of light. Plugging in the numbers, omega equals 1.22 times 10 to the 15 radians per second. Now suppose we break the perfect symmetry by introducing a 1% asymmetry. This means alpha equals 0.01. With the inverse quadratic scaling and a proportionality constant around 10 to the 4, we get Q approximately equals 10 to the 8. This is an extraordinarily high quality factor, achievable with just 1% asymmetry. What does this Q factor mean in terms of photon lifetime? The photon lifetime tau is related to Q by a simple formula. Tau equals Q over omega, with Q equals 10 to the 8, and omega equals 1.22 times 10 to the 15, we get tau equals 82 nanoseconds. That's an extremely long photon lifetime for a nanoscale cavity. Let's examine a specific practical example, a silicon photonic crystal slab. This is one of the most common platforms for realizing bound states in the continuum. Here's a silicon slab with a periodic array of holes forming a photonic crystal. The slab thickness is typically around 220 nanometers, and the holes have a radius of about 100 nanometers with a pitch of 400 nanometers. This structure has vertical mirror symmetry. Modes can be classified as transverse electric, with the electric field mainly in the plane, or transverse magnetic, with the magnetic field in the plane. For transverse electric-like modes with odd symmetry in the vertical direction, coupling to the radiation continuum is forbidden by symmetry. This creates a symmetry-protected bound state in the continuum at the gamma point in momentum space. Now let's ask an important question. What happens when we deliberately break the symmetry? This is actually useful because it allows us to control the coupling strength. If we make the holes elliptical instead of circular, we break the vertical mirror symmetry. Now the bound state in the continuum becomes quasi-bound with finite Q factor. The quality factor now scales as Q0 times the square of the ratio of minor axis r to eccentricity e. By controlling the ellipticity, we can tune Q over many orders of magnitude. This controlled symmetry breaking is extremely useful. It allows us to create cavities with designer Q factors. You can have ultra-high Q for strong light-matter interaction, or moderate Q for efficient outcoupling. Let me give you an analogy to build intuition. Imagine you're in a small shelter during a perfect storm. The storm represents the radiation continuum, chaotic, energetic, everywhere around you. You would expect the shelter to be battered and destroyed. But if the shelter is designed with perfect symmetry, and the storm has opposite symmetry, the forces cancel out perfectly. You remain completely safe despite being surrounded by chaos. That's a bound state in the continuum. Let's think about energy flow. In a bound state in the continuum, all the energy remains localized. This leads to enormous field enhancement, which is crucial for applications. The peak intensity I peak is proportional to Q times the input intensity. With Q values of 10 to the 6 or higher, you can achieve million-fold intensity enhancement. This field enhancement is what makes bound states in the continuum so attractive for nonlinear optics. Processes like harmonic generation, four-wave mixing, and parametric amplification all scale with intensity. For second harmonic generation, the generated power PSHG scales as intensity squared, which means it scales as Q squared. This quadratic enhancement is extremely powerful. Another fascinating aspect is dispersion engineering. Near a bound state in the continuum, the dispersion becomes highly engineerable. The group velocity, which describes how fast light pulses propagate, can be dramatically reduced near a bound state in the continuum. This is called slow light. The group velocity Vg equals d omega dk. Near the bound state in the continuum, the dispersion curve flattens and Vg approaches zero. Slow light means photons spend more time interacting with the material. This enhances nonlinear effects, sensing capabilities, and light-matter coupling strength. How do we experimentally verify that we've created a bound state in the continuum? There are several key signatures to look for. The first signature is the Fano-resonance line shape. When you scan the wavelength, the transmission spectrum shows a characteristic asymmetric profile. The transmission T omega equals the squared magnitude of epsilon plus q over epsilon plus I, where epsilon is the reduced energy and q is the Fano parameter. This asymmetric line shape is a fingerprint of interference between a discrete state and a continuum. The second signature is observing the q factor diverge as you tune toward the bound state in the continuum. You should see q scale as 1 over alpha squared, where alpha is your tuning parameter. The third signature, for topologically protected bound states, is measuring the winding of polarization in momentum space. This requires angle-resolved spectroscopy with polarization analysis. Let me now discuss the exciting applications enabled by bound states in the continuum. These ultra-high Q nanocavities are revolutionizing several fields. First is biosensing. The extreme field confinement and high Q allow detection of single molecules. When a molecule binds to the cavity surface, it shifts the resonance frequency. The frequency shift delta omega is proportional to the overlap between the field intensity and the permittivity change. High Q and small mode volume 5 maximize sensitivity. Second is nonlinear frequency conversion. The Q-squared enhancement makes it possible to achieve efficient harmonic generation and parametric processes with milliwatt-level pump powers. Third is quantum light sources. By coupling quantum emitters to bound state in the continuum modes, you can achieve strong Purcell enhancement and generate single photons or entangled photon pairs efficiently. The Purcell factor Fp equals 3 over 4 pi squared times lambda over n cubed times q over v. Both high Q and small v contribute to enormous Purcell enhancement. Fourth is lasing. The high Q dramatically reduces the lasing threshold. You can achieve ultra-low threshold nanolasers that operate with nanowatts of pump power. Of course, there are challenges in working with bound states in the continuum. Let me be honest about the limitations. First is fabrication precision. To achieve the predicted ultra-high Q factors, you need near-perfect fabrication. Any roughness or asymmetry will reduce Q. Surface roughness on the order of 1 nanometer can scatter light and break the bound state condition. This requires state-of-the-art nanofabrication techniques. Second is material absorption. Even if you have perfect structural design, material absorption sets a fundamental limit on Q. The total Q factor is limited by both radiation Q rad and absorption Q abs. In the bound state in the continuum, radiation Q is infinite, so absorption dominates. Third is the coupling challenge. With extremely high Q, the cavity is so well isolated that it's difficult to couple light in or out efficiently. You need carefully designed coupling structures. Let me give you the theoretical framework for understanding bound states in the continuum quantitatively. We use coupled mode theory. The amplitude A of the cavity mode evolves according to dA dt equals I omega 0 minus gamma times A plus kappa Sn, where omega 0 is the resonance frequency, gamma is the decay rate, and kappa is the coupling coefficient. The decay rate gamma equals the sum of radiative decay gamma rad and absorption decay gamma abs. For a bound state in the continuum, gamma rad equals 0. The coupling coefficient kappa controls how efficiently we can couple light into and out of the cavity. There's a trade-off. Stronger coupling means easier access but lower effective Q. The transmission T equals the squared magnitude of kappa squared over I times omega minus omega 0 plus gamma plus kappa squared. This gives the familiar Lorentzian line shape modified by the coupling. Let me touch on an advanced topic. The connection between bound states in the continuum and topological photonics. This is a cutting-edge research area. Bound states in the continuum in momentum space can carry topological charge, which is a robust integer characterizing the winding of eigenvectors around the bound state point. The topological charge C equals 1 over 2 pi times the contour integral of the gradient of the phase phi with respect to k dotted with dk. This charge is quantized and protected against perturbations. This topological protection is powerful. Small perturbations cannot destroy the bound state. They can only move it in momentum space. The total charge in a given region is conserved. Bound states with opposite topological charges can merge and annihilate each other. This process is analogous to particle-antiparticle annihilation in physics. How do we actually calculate these bound states numerically? There are two main approaches: finite difference time domain and rigorous coupled wave analysis. Finite difference time domain directly solves Maxwell's equations by discretizing space and time. You excite the structure with a pulse and watch the field decay. The decay time gives you Q. The quality factor Q equals omega 0 tau over 2, where tau is the field decay time constant. By fitting the exponential decay, you extract Q. Rigorous coupled wave analysis expands the fields in terms of diffraction orders and solves for the eigenmodes directly. This gives you complex frequencies, where the imaginary part is related to Q. Q equals the real part of omega, divided by 2 times the absolute value of the imaginary part. For a bound state in the continuum, the imaginary part approaches 0 and Q diverges. Let me compare bound states in the continuum with other high-Q photonic systems. How do they stack up? Whispering gallery mode resonators, like microspheres and toroids, can achieve Q factors up to 10 to the 11. But they're much larger, typically tens of microns. Traditional photonic crystal cavities achieve Q up to 10 to the 7 with very small mode volumes, but they're still limited by fundamental radiation losses. Bound state in the continuum cavities offer theoretically infinite Q while maintaining compact size. The key advantage is that Q is not fundamentally limited by radiation, only by material absorption and fabrication imperfections. The mode volume for bound state in the continuum modes can be on the order of 1 cubic wavelength or smaller. Combined with high Q, this gives unprecedented Q over V ratios for enhancing light matter interactions. Let me walk you through how you would actually realize a bound state in the continuum, experimentally. Step 1 is design. You use electromagnetic simulations to find the structural parameters that give a bound state in the continuum at your target wavelength. Step 2 is fabrication. You typically use electron beam lithography to pattern the nanostructure, followed by dry etching to transfer the pattern. Step 3 is optical characterization. You measure the transmission or reflection spectrum to identify the resonance and extract the Q factor from the line width. Step 4 is verification. You check that Q increases as you approach the bound state in the continuum condition, following the expected 1 over alpha squared scaling. Let me tell you about some real experimental achievements. In 2019, a research group demonstrated a photonic crystal slab with Q exceeding 10 to the 6. They used a silicon photonic crystal slab with carefully optimized hole shapes. The measured Q factor was 2.5 million, limited primarily by fabrication imperfections. The line width delta lambda equals lambda over Q, which gives 1550 nanometers divided by 2.5 million equals 0.62 picometers. This is an incredibly narrow resonance. With this ultra-narrow line width, they demonstrated biosensing with attomolar sensitivity, that's 10 to the minus 18 molar concentration. They could detect binding of individual protein molecules. Let me conclude by discussing future directions. There are many exciting open questions in this field. First question, can we reach Q factors of 10 to the 9 or higher experimentally? This would require nearly perfect fabrication and ultra-low loss materials. Some researchers are exploring crystalline materials and cryogenic operation. Second question, can we make dynamically tunable bound states in the continuum? Imagine being able to switch Q on and off electrically or optically. This would enable new modulation and switching schemes. Third question, can we realize bound states in the continuum in fully three-dimensional structures? Most work focuses on two-dimensional slabs. True 3D structures might offer new functionalities. Fourth question, what are the ultimate quantum limits? Can we use bound states in the continuum for quantum information processing, or to study fundamental quantum optics in new regimes? Let me summarize the key concepts we've covered today. Bound states in the continuum are localized optical modes that exist at the same frequency as extended radiating modes, but remain perfectly confined. 3 mechanisms enable bound states in the continuum: symmetry protection, Friedrich-Wintgen interference, and topological protection. The quality factor scales as 1 over alpha squared near the bound state condition, enabling ultra-high Q with small perturbations. Applications span biosensing, nonlinear optics, quantum light sources, and ultra-low threshold lasers. The main challenges are fabrication precision and intrinsic material absorption, which set practical limits on achievable Q factors. Bound states in the continuum represent an exciting frontier connecting topological physics and photonics, with many open questions remaining. Thank you for your attention. I hope this lecture has given you a deep understanding of bound states in the continuum in nanocavities and inspired you to think about how we can trap light in seemingly impossible ways. The field is rapidly evolving, and I encourage you to explore the literature and perhaps contribute your own ideas to this fascinating area of nanophotonics.